So let's prove the second half now, the quadratic lower bound. With these two parts, we're going to be able to show that the two lines of the lower bound and the upper bound meet, and we'll have a finite limit on the number of iterations that PLA takes to converge. So we're going to say at iteration k, we have a weight vector that was updated from the last weight vector at iteration k minus 1 by adding in the misclassified point from the k minus 1 interval. So we can expand this out. We're going to take this first term and just to make sure everything is here, I'm just going to write down the second term. You can see where we're going with this, right? Every time what we're doing is we're taking the first term and expanding it out into two terms, just like we did before. And we're working back from the kth iteration all the way back to the first iteration, or the 0th iteration, where our initial weight vector is written like that. And just like we did before, we're going to take all of these different terms and we're going to sum them together. So you're going to use the index I from the 0th iteration all the way to the k minus 1. And it's basically just all of the points that we've missed put together. Okay, so far? Okay, so now we're going to employ a trick. We're going to remember that this data set is linearly separable. That was one of the assumptions we made to make sure that PLA converges, right? In this case, we know that there is a set of weights, we're going to call it theta star, that's guaranteed to separate both classes correctly. We're going to multiply both sides of this equation by theta star. So expanding out, we're going to get something like this. Right, where I've just multiplied the theta star through on both sides. Okay, so far that doesn't help us so much, but we're going to define a specific quantity that was going to help us with a lower bound. That's going to be gamma. I'm going to define that just to be the minimum of these terms here. Okay, so out of all the points in my data set, I'm going to find the one that has the smallest value. Okay, well actually doesn't matter. Well, this is just an IF value here. Okay, so what's interesting about this value is it has a meaning. Gamma we can think about is a margin between the distance of the hyperplane defined by a set of weights and a particular point, right? So we're iterating through this quantity over all of the points, right? So for example, let's take a look at this red X here. We're going to say that the gamma defined here, okay, not the minimum part, okay, this particular term here is just the distance value between the point and the hyperplane defined by that particular set of weights, theta. So when we take the minimum of these, okay, of all of these margins, so here's a margin, here's a margin, here's a margin, okay, and we find the minimum one, this is somehow defining how much wiggle room we have to go between the hyperplane. So it helps to take a look at another diagram. So here on the left, we have a case where we have a larger margin. This is the same diagram as we showed you earlier, where basically there's quite a lot of separation between the points. So whether we draw the perceptron boundary as marked here, or over here, or over here, these are all going to get perfect classification accuracy. So there's a lot of different planes to pick here. When we have a fairly small margin, as you can see here, there's not as much separation. There's not going to be as much wiggle room to define where the perceptron can put its hyperplane as defined by theta, right? So you can see in this case, we would think of this one as an easier case and this one as a harder case. So what we're going to do now is we're going to take this side and switch it over to the left-hand side, and we're going to take the left-hand side and put it on the right. And this is because this quantity is going to be more fixed. So what do we have here? We're going to ignore the zero vector, and we're going to take this part and substitute it for the gamma that we saw. So we have a gamma, and we have how many of them? Well, we have a summation here, so we're going to have k of them. And because there's a minimum here that's defined, it's going to have to be less than or equal to the right-hand side, right? So we're going to just take this left-hand side and switch it over here. We're going to write it out. And we're going to invoke the Cauchy-Schwarz inequality for the next step, which basically says we can take the square and the norms and then set them equal to each other. Okay, so we still have this inequality of being less than here. So that's going to allow us to take the square this is what we just invoked. And then we're going to just break these two terms apart. And then from our upper bound, we know something about this first quantity. Namely, that it was equal to k times the maximum value of the norm over all of the iterations. So this part is from the upper bound that we showed earlier. So we spelled this out for you on this slide, so you can see all the steps. And we're going to make one final part. So I'm going to take this equation and move it up. So we have these two parts. I'm going to solve for k. So we have these one take out, right? And so we're going to end up with m S norm squared over gamma squared. And what does this mean? It means that we know there's a bound for k. It cannot be over this amount, right? So this is going to be some finite number of iterations, and that gives us a maximum bound. So an important thing to note is how k varies. We note that k is proportional to the margin squared, which is telling us that when we have a smaller room for finding a good dividing line, it's going to be exponentially harder to find a satisfying separator. Note that when we find a satisfying separator, it doesn't mean that we're going to get an optimal separator. It could be any one of the planes that we saw earlier. So for example, even though we might find a nice plane like the one here, it's quite possible that we find one that's not so nice, like that, or one that even looks like this. All we're saying is that by the kth iteration, a satisfying hyperplane will be found. So great job going through the perceptron proof. Now you see we have an upper bound that is a linear bound, and a lower bound is a quadratic bound, and at some point they're going to meet. And that part is where we have a maximum number of iterations. Now again, you need to remember that there's the definition of a margin, this gamma variable that we defined. This is going to prove incredibly useful later when we get to support vector machines, because as you noted towards the end, we only decided that we could get to a satisficing hyperplane, but certain hyperplanes might be better than others, even though all of them separate the binary data set just fine. We'll see how this works out in the second half of our course. See you later.